Okay, so now we have learned a little bit of theory of machine learning. So we know what is the difference between the regression and classification, and what the optimal decision rules are for regression and classification. So we know what supervised machine learning is and what is unsupervised machine learning. So now let us talk a little bit about the actual models. So recall that in machine learning, so we assume that the true underlying process that governs our data is y equals f of x plus epsilon, but the real f is not known, and instead what we try to do, so we kind of try to write it, try to replace it with some f hat of x, approximately. And how to construct this f hat of x, this is what our course is going to be about. So and now let us talk about simple methods to construct f hat. So the first of them is something familiar, is linear regression. This is something that you learned in regression analysis. This is the formula, so it is just a linear function in features, or a linear function in predictors. So here is an example, and I'm sure that that almost all of you took some form of regression analysis, and you learned how to fit linear models in R. So it's just a single comment in R, and what it returns is the set of coefficients. So this intercept is beta 0, this TV is going to be beta 1, this is going to be beta 2, and this newspaper is going to be beta 3. So you also learned how to, how to do it theoretically. We will review it in the next lecture. But now, just a bit of intuition. So the values of beta 0, beta 1, and so on up to beta p that are most consistent with the observed data means that we minimize the mean squared error. So we find the values of model parameters that minimize the mean squared error of the model. So just for an example, so if we consider a hypothetical alternative model, right? So instead of the values of these parameters that we found in R, so I just took some random numbers, then these are predictions. And of course, sometimes my alternative model could be better for some observations, like here. So it is closer to the observed value sometimes, right? So this is y hat is the fitted linear model in R, and y alt is the alternative model that is just a bunch of random numbers. So the mean squared error here are these numbers, 2.78, and the main point here is that the linear model error, the error of the linear model, is always going to be smaller. So this is how it is constructed. It's by definition of a linear regression. So linear regression is a parametric model, right? So we first assume some kind of specific general form of the model with parameters, and then we find parameter values minimizing the mean squared error. So hypothetically, it could be some other general form. So like, I don't know, maybe we could write something like beta 0 plus beta 1 x 1 divided by beta 2 plus beta 3 x, I don't know, 2 times x3 to the power beta 4, something like this. So anything of this form would be a parametric model. So we first assume kind of the general form of the model, and then we find values of parameters to minimize the error. So an alternative, so later we're going to learn about other parametric models, and the most complex, the kind of the quintessence of parametric modeling, is an artificial neural network. This is what modern deep learning is based on. So this is an extremely complex, but it's still a parametric model. So the underlying idea is still the same, that there's going to be a lot of parameters, maybe hundreds of millions of parameters, but it's still a lot of parameters. And by a clever algorithm, we find values of parameters that minimize the error. So, and non-parametric models are kind of a bit different in the sense that we do not assume an explicit functional form of f hat. How does it work? We will see later. So one of them is a very simple, is so-called k-nearest neighbors. More complex and more sophisticated, more powerful models are random forest and support vector machine that we are going to learn in a few weeks. So now, quiz about the linear regression.